Shoes on. I did. Good evening, and welcome to tonight's Key School program. I'm very happy to introduce our speaker for tonight, Robert M. Breiber, on the topic of materials for the future. Rob received his BS in Materials Science and Engineering at Cornell University and his PhD in Polymer Science and Engineering at the University of Massachusetts. He's an emeritus professor of Materials Science and Engineering at the University of Maryland, and he is a past president of the Neutron Scattering Society of America, a fellow of the American Physical Society and the Neutron Scattering Society of America, a recipient of the Department of Commerce Bronze Medal, a former editor of the Journal of Polymer Science, Polymer Physics, and a University of Maryland Distinguished Scholar Teacher. So let's welcome Rob Breiber.
Thank you very much. Rhoda indicated I am a emeritus faculty member. I should tell you that's about 6 weeks old. So it's a relatively recent transition. It's a pleasure for me to be here today. You may have noticed I have a table next to me with a lot of things on it. So we're going to have a little fun today as well and show you some demonstrations. But I'm going to start off by talking a little bit about material science and engineering as a discipline, and then get into some of the more fun aspects. So first thing, the field of material science and engineering, it tries to synthesize all the different disciplines of engineering, physics, chemistry, and biology to advance technology. And the idea is that materials engineers and materials scientists develop materials and material systems with exceptional properties to enable technological advancement in all fields of engineering. If you want better medical implants, you often need better materials. If you want better batteries, you need better materials. If you want better roads, you may need better materials to make those roads out of. And the list goes on and on. The material science and engineers, they study the science behind the structure, property relations. How does the structure relate to the final properties of that material? And they understand how the atomic, molecular, nanoscale, and microscale structure relates to their final end use. A number of years ago, the National Academy of Engineering looked at what the future would bring and what engineers were going to have to work on and what are some of the major problems they're going to have to deal with. The goals of that study were to improve sustainability for the world, improve security for the world, improve the health, and improve the quality of life for all people. And they made a list of 14 different areas that people are going to have major problems they're going to have to solve. And I listed those 14 areas here, and I put a number of them in green to show you where material science and engineering and the development of new materials would play a key role in solving these grand societal problems. If we think about it for a little bit, if we go back in history, even our historical names are named after materials. I think you can all start off with the oldest material. Stone, the Stone Age, right? The Stone Age. And then comes the Bronze Age, and then comes the Iron Age, and we go into the Modern Age. So if I were to ask you, what material might you name the modern age after? Plastics, that's one. Silicon, that's another. Well, we'll talk about plastics quite a bit, but since silicon is such a key aspect of materials in our current future, since it's such an important material, I thought I'd actually hand around some pieces of silicon because many people have not actually held pure silicon in their hand before. And I'll just pass this around. You can just pass it to your neighbor. So silicon is essentially the purest material that people make nowadays, because if you want to build the best computer chips, you have to have essentially atomic control over the structure and purity of the material to make chips at the current highest technological level. So this is a piece of a single crystal of silicon. It's actually grown from a mat of molten silicon as what's called a boule, which is basically a long rod. And this has been chopped up. And it's one perfect single crystal. And then it's been chopped up into a chunk of silicon about 4 inches in diameter and about half an inch thick. So I'll pass this around, just take a look at it. Pass another one around here. Now, a 4-inch piece of silicon is not what's current at the technological, current modern technologies. So if you actually go into a fabrication facility where Intel makes chips or Taiwan Semiconductor Manufacturing makes chips, they work on pieces of silicon like this. So obviously much bigger, quite thin because you don't want to waste the silicon and you're making computer chips. You can imagine this as almost like a tree of silicon, one perfect single crystal, this big in diameter but many feet long, sliced up with a diamond saw into wafers like this, mechanically and chemically polished to be atomically smooth. So it's looks like a perfect mirror here. And then they fabricate circuitry on this by implanting different elements to change the conductivity of it, and essentially write circuitry into the silicon like that. So this is what you would find in a modern modern chip factory. Now, in a modern chip factory, no one would actually hold this in their hand because you've already contaminated it. It's all done by robotics, but I can hold this in my hand because we're not going to try to make computer chips out of this piece of silicon. So, as you guys came up with, we would probably call the modern age either the age of silicon or the age of plastics. Those are two obvious logical choices for that. Most advances in materials have occurred in the past 200 years or so. And so most of the modern materials that you see and interact with every day are actually quite recent advances. So the bottom line is everything is made out of stuff, one way or another. We have the ages of man, as we just talked about: stone, copper, bronze, iron, silicon, maybe polymers. Think about it for a minute. Most technological advances involve advances in new materials. If you want a better light bulb, you need a filament, or even the invention of the light bulb, you need a filament that radiates light but doesn't burn up. If you want a telephone, you need wires and diaphragm to convert sound to electrical impulses and then back again. If you want an airplane, the Wright brothers created the first aluminum engine. If you want better airplanes, i.e. jets, you need nickel superalloys or some similar material that can survive at very high temperatures with very well-known properties, so they don't expand in the wrong direction, they don't fail catastrophically at the wrong time, they can operate at 1,000 degrees, etc. You want computers, you need perfectly pure silicon like we're passing around, or I showed you up here, to make silicon transistors. You need materials that show giant magnetoresistive effects to make hard disk drives. You need carbon fiber composites to make fancy sports equipment. You need better shape memory alloys, polymers, titanium for medical devices and implants. Basically, necessity for new inventions requires invention of new materials, or understanding and developing those new materials. How do I select a material for a new application? Well, I need to define my application. I need to determine the required material properties for the best performance. So what does that material have to do? What does the application require of that material? I screen candidates or choose, or maybe I have to develop a new material to meet that application. Maybe it doesn't exist. Maybe I need some kind of combination of properties that I can't find in any current material. So I have to go out and say, I need some of this and I need some of that, and I try to put it together. Maybe that means a new material, or maybe that means a composite of different materials. Depends on the application, depends on what materials you have available. For example, how about I need an inexpensive container for a carbonated beverage that allows cooling, transportation, storage, and maximum product lifetime? There are several workable choices. Oh, we could have glass. We could have metal. We could have plastic. All trying to solve the same problem, but each one with potential limitations. So you think about it a little bit. We see, if you go into a store, you may see all three of those simultaneously, but they all have certain limitations and certain advantages to them. There may be ease of recyclability, it may be weight, it may be price, depends on what's the controlling aspect in a particular application. So in the worldview of material scientists, the material scientist likes to break the world up into different classes of materials. The three biggest classes that materials get broken up into are metals, polymers, and ceramics. We can also have things like semiconductors, which is related to the piece of silicon that's being passed around, where you can control the conductivity from being an insulator to being a conductor, allowing you to essentially write circuitry into the silicon. Or, for example, biomaterials, which generally fall into either ceramics, polymers, or metals, but have very specialized applications to be compatible with biology, and often involve composites of these different materials together in the area of biomaterials. But it may also be completely from nature and not man-made, as in many of these, or extracted from the earth, as in many of those. So let's talk about each of these three main classes in turn. Let's talk about metals, let's talk about ceramics, and let's talk about polymers. Let's talk about some interesting examples in each of these cases. So let's first take a little time and talk about metals. So first thing I want to talk about are magnets. So neodymium iron boron magnets. These are really strong magnets. These are the strongest magnets we currently have, and form the basis of quite a few interesting technologies. In this graph in the upper left shows the performance of magnets as a function of time, a function of history for about the last 100 years. And this shows you different magnetic materials improving over time up to these modern neodymium iron boron magnets, or NIB magnets. These are very strong magnets. I'll show a video here, but I'll also show you with my hand here. So here's a video, and here's the same thing right here. So you can watch the video as well. So I'm not going to pass these around. They're a little bit, sometimes I do, but I'll tell you a few things. One, they're a little bit dangerous because if they go down into this part of your hand, we will generally know because you'll yell out loudly because it hurts. It hurts a lot. The other thing is if you drop it, they will fly across the floor, and if the legs of your chair are iron or steel-based, they'll slam into it, they'll make a loud crack, and we'll know who dropped the magnet. But if you're interested, please come up afterwards and you can see. They're actually, if you put them together, you actually have to be very careful because you'll get some skin pinched between them if you don't hold them very tightly and let them come together. But once they're together, you can come up and try to pull them apart because they're really actually quite hard to pull apart. And so feel free to come up afterwards and look at these. The other thing is that there's a property called Lenz's law, which says that if I have a moving magnetic field near a conductor, I will get eddy currents in the conductor, which will create an induced magnetic field that opposes the moving original magnetic field. So I have a piece of copper here and a piece of plastic. Copper is a good conductor. It's what we wire our houses with. It's what the wires, it's used in wiring in this building and everywhere else. Plastic is a good insulator. It's actually what we insulate wires with on the outside to prevent short circuits. If I take this magnet and drop it into this copper tube, I have a demonstration of Lenz's law, which allows the magnet to fall through the tube, but the induced magnetic field opposes the falling magnet, and it falls, but actually only very slowly. And again, I encourage you to come up afterwards and look at this. I have a couple of these, so feel free. It's very interesting. If you drop the magnet straight down in and watch, and you can put your hand here. If you put your hand there, you can't see anything. So you leave it down a little bit, and you can literally see the magnet floating down through the copper tube. It wobbles a little on the way down because it gets closer to the side of the copper. The induced magnetic field's increased a little bit. It pushes it back to the middle. So it tries to stay in the middle, wobbling as it falls through. Now, of course, if I have an insulator, a non-conductor, I don't get that Lenz's law effect. It just falls right through. So there are no tricks there. Well, one, it works. The other one, it doesn't. So one of the interesting things is that uh, these magnets form the basis for many modern technologies. In hard disk drives, you'll probably notice that any car you buy now pretty much always has power windows. You don't see hand crank windows very much anymore because these kinds of magnets allow for very efficient electric motors relatively cheaply, very compact, easy to make a very small motor. Electric cars with regenerative braking and that will use these materials. Neodymium is a critical, a rare earth element, controlled mostly, mined in China. So there's a lot of concern about control on the world scale of who has neodymium because it's such an important technological element for this type of application. So there's just a little graph here from about 10 years ago showing the potential changes in the price of magnets due to due to the price of neodymium controlling that. So there's a lot of concern in the world stage about who has the mines, who's willing to mine it, what are the economics of controlling critical elements like neodymium. So another one, nickel titanium alloy. So this is called a shape memory alloy. This is a material that has a crystal-crystal phase transformation that allows you to deform it, and it remembers its original shape, and it will reverse that through a crystal or a crystal-crystal transformation or a cooperative motion of the atoms within the crystal from one shape to another shape. And so again, this is going to be a little bit hard to see because everything's a little bit small, but I have a video. And again, I have some demonstrations that can be done up at the afterwards if someone wants to come up and look at this in more detail. But I have a paper clip made of nickel titanium. And one should note that this alloy was discovered in 1959 at the Naval Ordnance Lab in White Oak, Maryland. And the name nickel titanium Naval Ordnance Lab is what spells out nitinol. And so that's where the name nitinol for the nickel titanium alloy came from. So here's the video, here's the paper clip, and here's my version of that paper clip. And I will unbend this paper clip, and then I will also show the video. And the heat from a hair dryer will allow this paper clip, which has been mostly straightened out here, to recover its shape. I'll try to hold this up in the light, and let me also start the video simultaneously. I think right here, I can sort of show it right here. It's caught in the light, but you'll see it better with at least as well with the video. And it wound itself right back up to the original paperclip size. So you can see there's the paperclip. tweezers is not because the hairdryer is too hot. It's just so it can hold it conveniently. And it goes right back to its original shape. So what are some ideas that this could be used for? So my students often say, oh, if I had a car with nickel titanium bumpers, I could have a little accident in the parking lot and hop out with my hairdryer and take out the dent. So these things are actually used in stents. So because you can control the temperature at which, but through composition over which these materials activate. And so you can have it so it's kept cold, and then at room temperature or body temperature, it will open up. So you can have a stent that's compressed down, put into the artery or vein, and then at body temperature, it will expand out and open up the artery or the vein. And another interesting application is shown in this video here. We have a windmill with a hot water source down here, and then air cooling on top, and a loop of this shape memory alloy going around these two pulleys. And when it goes into the water, there's a contraction of on the order of 5% in length. And when it comes out of the water, it cools off and expands, and that will drive a motor. So you can see this windmill spinning with just the heat differential between the hot water in this cup here and air cooling on top is enough to drive it. Now this is a type of phase transition, and our refrigeration also works on a phase transition. Only typical refrigeration works on evaporation and condensation. But we have people at the University of Maryland working actually on a just funded large NSF center in collaboration with many other universities. And one of the projects that being worked on by a faculty member at the University of Maryland is using the same idea of a phase transition, but completely solid state, to make a solid state refrigerator based on shape memory alloys. And the thermodynamics says it can be potentially as efficient or even more efficient than current evaporation condensation, but without the potential escape of the coolant that occurs in conventional refrigerators. The economics are not there yet, because economics of refrigeration and air conditioning in particular have scaled so much that it's very inexpensive. But with hope over time, it could come down, and with hope over developing potentially even more efficient shape change alloys that operate at lower stresses, it could actually become commercial reality. So let's talk a little bit about ceramics. So the ceramic I want to talk about first, or actually the one I will talk about now, are superconducting materials. I want to talk about, in particular, a superconductor made out of yttrium barium copper oxide, which is very well known in the superconducting community, often called YBCO. This is what's called a high temperature superconductor, and caused a huge amount of excitement in the scientific literature when it was first discovered. Now, this operates at a temperature of around liquid nitrogen, which is minus 321 degrees Fahrenheit or minus 196 degrees centigrade. Most of the world would not call that high temperature, because most of the world would say that's still pretty darn cold. But prior to the discovery of this class of materials, high temperature superconductors, they only really knew about superconductors that were very close to absolute zero, with significantly lower temperatures than this. One of the very interesting so these are used, for example, in superconducting MRI machines for medical imaging. There's actually been a demonstration of a Japanese superconducting train on a superconducting rail, and that's based on a very interesting property when these materials are superconducting, is they reject magnetic fields. And so that means that if I take one of these really strong magnets, these neodymium iron magnets, and put it above one of these superconductors, and this is a disk of yttrium barium copper oxide sitting in a pool of liquid nitrogen with a neodymium iron boron magnet above it. The magnetic field is being rejected by the yttrium barium copper oxide, and you actually get magnetic levitation. And you'll see here in a minute, you'll see the liquid nitrogen actually bubbling around the piece of yttrium barium copper oxide, and there's one of these magnets. And it levitates above the superconductor. And as long as this liquid nitrogen is here, keeping the superconductor cold, that will stay levitating. As the liquid nitrogen boils away, the superconducting material will go through its transition, no longer be a superconductor, and you'll no longer have this effect, and the magnet will, of course, will fall off. But if you keep it cold, it can work. Now, one of the interesting phenomenological observations is that early superconductors, which were here's a plot of temperature at which a material becomes superconducting versus the number of elements in that superconductor. This is a phenomenological observation. There's nothing significant theory behind it, but it says that some pure elements can become superconducting right down very close to absolute zero at minus essentially 460, slightly less, 460 degrees Fahrenheit or 273 degrees centigrade. As the system gets more complex, we've seen observation of increasing superconducting transition to where we can get to, if cooled by liquid nitrogen, they remain superconducting. So this is yttrium barium copper oxide and some more complex materials. There's been for the last 50, 60 years an interest in pushing this higher and higher. Could we ever get to a room temperature superconductor? Okay. Could we ever get to a room temperature superconductor? I postulate that, well, this has been of huge interest to scientists and engineers and people with money to invest in this kind of thing for a long time. Because if you did discover a room temperature superconductor, you would change the world because you would change the way we store and transmit electricity. You would win the Nobel Prize, and you become a billionaire. All of those things are strong motivating factors for a lot of people. But we don't have a room temperature superconductor. There's been discussion of potential room temperature or higher temperature ones at very high pressure. But what we really want is a material that is superconducting at room temperature, at atmospheric pressure, under atmospheric conditions, things like that. So there's a real desire for that. Now, that doesn't mean that Hollywood hasn't thought of this already. And it's actually shown up in a popular movie. You may not realize this, but there was a movie going back almost 15 years ago now called Avatar, which was a science fiction movie. The premise of Avatar was it was in the future and that the humans had gone off to the planet Pandora and they were mining a material on the planet Pandora. Does anybody remember what that material was called? It was called unobtainium. Now, it's not obvious in the regular theatrical release what unobtainium was, but if you buy the director's edition box set DVD with all the extras on it, you actually realize that if I play this clip,
Right. Come here. Come here. I can't. This is why we're here. Unobtainium. Unobtainium. Because this little gray rock sells for 20 million a kilo. That's the only reason. It's what pays for the whole party. It's what pays for your science. Comprendo?
So where are we going?
Getting out of Dodge. I'm not about to let Selfridge and Quaritch micromanage this thing. There's a mobile link up at Site 26 we can work out of, way up in the mountains.
The Hallelujah Mountains?
That's right.
Are you serious?
Yeah.
Yes! The legendary floating mountains of Pandora? Heard of them?
instruments.
Yep, we're in the flux vortex.
VFR from here on.
What's VFR?
Means you gotta see where you're going.
Can't see anything.
Exactly. Ain't that a bitch?
Oh my God.
You should see your faces. Thank you for flying Air Pandora.
Yeah, so what does hold them up? Grace explained it to me. Some kind of maglev effect, because unobtainium is a superconductor. Or something.
Premise here is that we've flown across the galaxy to mine unobtainium off the planet Pandora, and that the floating Hallelujah Mountains on the planet are high-grade unobtainium ore levitating in the planet's magnetic field. Now, that's a pretty strong magnetic field on that planet. Probably pull the iron out of the pilot's blood, but whatever. Uh, this is Hollywood. But they did make an attempt, even though they didn't tell you in the theatrical release, that unobtainium was a room temperature superconductor. And as I said, that is a strong motivating factor to have a room temperature superconductor, enough, in a sense, to base the premise of a movie on, even though in the actual theatrical release they sort of left that part out. It just left it as unobtainium without actually telling you what the point of unobtainium was. So let's talk a little bit about polymers. So the basics of polymers is that a polymer is a long chain molecule made of many repeat units or monomers, and a high molecular weight polymer chain can have up to 10,000, 100,000, or even more of these monomers along the chain. And that a simple polymer chain might look like this squiggle here, though this would be relatively short. And from a chemical point of view, not necessarily from the chemistry point of view of making it, but just from the chemical point of view, probably the simplest one is just a series of carbon atoms connected together along a backbone with, carbon likes to have 4 bonds to it, so it would have 2 hydrogens, and that's just polyethylene. And if you start putting carbon atoms together, of course, if you just have 1 carbon atom, we call that methane, it's a gas. If we have 2, that's ethane, also a gas. If we have 3, that's propane, you run your grill off of that. If you have 6 to 12, you have gasoline. If you have 20 to 40, you have paraffin. If you have 5,000 more, you have polyethylene. So what you're running your grill off of, what you're driving your car off of, and what's polyethylene are essentially chemically all almost the same. So if you have 200,000 or more, then you have something called ultra high molecular weight polyethylene. This is actually used in biomedical implants quite a bit. It's often in a joint, the low friction surface that forms the socket or a ball joint in an implant, be it a shoulder or a hip or something like that, or a knee, something like that. It has very good wear properties. So this demonstration I like to call a polymer in a can. So this is to give you a little bit of idea of how long polymer chains can be. So this is my polymer in a can here. So this is a polymer chain. I really didn't have to do very much there. So it turns out that this polymer chain here, which is obviously a lot longer than that squiggle I had back here, is not long enough if it was polyethylene to make a decent garbage bag. It would probably have to be 3 to 4 times longer than this to make a decent garbage bag. You can imagine that these beads, each black and white one, each one is a carbon atom, and 2 of them form the typical monomer of 2 carbon atoms. But this chain, which seems pretty long qualitatively, is not really very long compared to a typical polymer that you would find in everyday life in an application. So just for example, this has about 5,700 beads in that chain. If I had ultra-high molecular weight polyethylene, I would expect at least 100,000 beads in the chain. And if I scaled that up a molecule of ultra-high molecular weight polyethylene to a string of beads like this, it would be about 3/4 of a mile long. Then if I look at, say, the human DNA chromosome, the first one, which is the largest, which has about 250 million base pairs, each one is about 0.34 nanometers in size. The actual DNA, DNA chromosome molecule is about 3 inches long. If I scale that up to a string of beads, it's almost 1,000 miles long. So these polymer molecules, be they synthetic or probably the most complex one in the human genome, the first chromosome, are really long molecules. And that gives them a lot of unusual properties. So one thing I'd like to talk briefly about is the idea of hard materials versus soft materials. We've talked about metals, ceramics, and polymers. Those are sort of 3 classes. But we can also break things up into the idea of hard materials and soft materials. We typically put metals and ceramics into the idea of hard materials, and we put polymers and rubber bands, which many of you have in your hand, into the idea of soft materials. Now, when I stretch a material or put a force on a material, the way or the thermodynamics behind the way a hard material like a metal or a ceramic behaves versus a soft material are different. In a hard material, when I stretch it, I directly stretch the atomic bonds. So if I take a hard material here, a nice crystalline ceramic or metal, and I stretch it, I stretch the bonds between the atoms, and I end up with a increase in the internal energy, and that increase results in a force pulling back that I feel when I try to stretch it, and that's the force trying to lower the internal energy of the material. When I stretch a rubber band like this, I'm not stretching the bonds directly. I'm taking the chain, which is typically sort of like this, and I'm just unwrapping it a little bit. Turns out that lowers the entropy of the system. And the second law of thermodynamics says the entropy wants to increase. And so that results in a force pulling back when you stretch your rubber band. So what you have here in your rubber band is very different. So take out your rubber bands and stretch them. You're feeling entropy when you stretch a rubber band. So now you're going to follow after me. And I'm going to make sure you all listen carefully. You're going to point your rubber band up in the air, and you're going to stretch it up in the air because you have people in front of you. And you're going to let it go, and we're going to go 1, 2, 3, and we're going to shout entropy. All right? Ready? 1, 2, 3, entropy. Now, for the thermodynamicists in the audience, you probably know there's another type of entropy occurred there because the rubber bands were all in a nice orderly array here, and now they're scattered all over the place. But all right. So the rubber band is an entropic spring. So you can go home and see your family, and you can tell them, watch this, I have an entropic spring. And you could shoot them with a rubber band. All right. So here's another interesting effect of controlling the properties of materials, of polymers. I have 2 rubber balls here. One is made of polyisoprene, and one is made of a polymer called norbornene. They have essentially the same density. They're both made up of carbon and hydrogen, so the same atoms, but they're connected in a different chemical formula. And that changes dramatically the mechanical properties of those materials. I'm going to drop them. It'll be a little hard to see, but I'll play this video. I'm going to drop them at the same time. Because they have the same elements of carbon and hydrogen in them, just arranged differently, they're the same size, they have the same density, so they have the same mass. They'll fall at the same speed. They'll hit the table. They'll start with the same potential energy up here, and they'll land on the stage here with the same kinetic energy. And then what happens to that kinetic energy when they hit the stage? One of them bounces and one of them doesn't. So playing the video, you'll see here, you'll see here, one of them bounces and one of them doesn't. Sorry, I'll play it again. One of them bounces and one of them doesn't. So they start with the same potential energy. They hit the table, or they hit the table here, or they hit the floor here with the same kinetic energy. But one of them, most of the energy dissipates in some manner, and one of them, most of the energy, or at least a good fraction of it, returns back to the ball, and it keeps bouncing. Oop. Where does the energy go? Heat. Also, sound. It's quite a bit louder than the other one. And in fact, they're actually quite good at absorbing energy. I can go here and I can take this and I can throw it pretty hard and it really doesn't go anywhere. Well, of course, if I throw this one even modestly hard, it bounces right up. And I can throw this one quite hard and it doesn't. Feel free to come up afterwards and bounce them a little bit. Another interesting property. I'm going to mix polymer and water and make a bottle of goop. So you can see this video here. It's quite viscous. Now, I have a table next to the video showing how much polymer and how much water and a bunch of choices. 1% polymer, 99% water. 5% polymer, 95% water. 10%, 90, 25, 75, 50, 50, all the way down to, well, 98, should be 99, sorry, typo there. 99% polymer and 1% water. I'm going to read through these, and I want you to raise your hand, and I'll even pretend we're in Chicago and you can vote more than once. All right. Which one you think the composition of this bottle of goop is? Is it 1% polymer, 99% water? Raise your hand. All right, I got about 4 people. 5%, oops, oh, darn. All right. I hit the wrong button. So the answer for those 5% people was 1% polymer, 99% water. I was hoping to get through the rest of the audience, but I revealed the secret beforehand. So much for having too many buttons on my remote. So this is only 1% polymer, which means just a little bit of polymer in the bottom of this jar, the rest filled with water, and it forms this goop. Why is that? Well, this is a very high molecular weight polymer, really long polymer chains, like the ultra high molecular weight polyethylene, only in a water soluble polymer. Polyethylene's not water soluble, so technically this is polyethylene oxide, but it's a very high molecular weight polymer. So even dissolved at 1% in this liquid, the polymer chains are still all entangled with each other and causing very high viscosity of this liquid. So just a pinch of polymer is enough to change the viscosity dramatically. So my last demonstration here is the idea of, first I have to talk a little bit about the concept of a polymer solution versus a polymer gel. So this is a polymer solution. The individual molecules are separate from each other, but they're entangled in the fluid. So it forms a liquid, and it's a very viscous liquid, sort of like honey, but it's still a liquid. If I take the individual polymer chains, which I show here, and I just made one red just to sort of highlight it, and I put in chemical bonds between the polymer chains. Unfortunately, it's a little hard to see, but there are little dots between these. So if I pull on one polymer chain, I can't pull it away from the others. If I grab this red one and pulled, I could essentially with molecular tweezers pull it out and separate it from the other ones. In this one, because I've chemically put chemical bonds across the chains, which are called chemical crosslinks. If I pull on one, it stays tied in like a fishing net or like with knots between them, so I can't separate it out anymore. If I take this form where the polymer chains are not connected to each other but just enmeshed, and I put it in a liquid that dissolves it, I get a solution of goop. If I take this one and I put it in, if I start with a cube, this cube dissolves and forms this goopy solution. If I take this cube and put it in, I get the cube swells up but stays a cube. It absorbs the water, but the polymer chains can't separate from each other, so it retains its shape, just becomes bigger like a sponge because it soaked up the water or soaked up the solvent, the liquid, and becomes a bigger cube. And so this forms actually the basis for some fairly important technologies. And I'll show you this. I'm missing one bottle. Well, that's a little unfortunate. Oh well, I have most of what I need, but I'm missing one part of it. So I have here some polymer that's been cross-linked. I'm going to put a little bit and I have here some water. I'm just going to dump one in the other. So what happened, I had particles just like that cube on the screen here. This cube, only I had little particles. I put them in the bottom of the jar and I dumped water on it, and all the little particles swelled up dramatically. And they're still here, but they're all packed together and they absorb the water. And now it behaves like a solid. If I had some salt water, which I forgot to bring, or I had it, I'm not sure where it went, I could actually collapse them back to particles again. But if I stick my finger in here, I can still push the particles around. So this is what we call a super absorbent polymer. It can absorb easily 100 times its weight in water. So very and very rapidly, obviously, too, because the particles are small with a high surface area, so you can have very rapid diffusion of the water into the into the particles and very dramatic swelling. So, what are the uses of superabsorbent polymers? Ideas? Yes. Yes, you could prevent plugs coming into your house. You could control water. Yes. Carbon dioxide absorbs it. Okay. Baby diapers. Yep. So diapers, water retention, whether it's your house or in agriculture, spill cleanup, again, that sort of thing. Artificial snow in movies is what they use to make this material. So one more example of a material from movies. This is a somewhat of a silly example, but it's in the realm of polymers. So let me play this little clip, which is actually technically it's a TV show. It's from
A nesting consciousness. That's it, inside the vat. A living plastic creature.
Well then, tip in your antiplastic and let's go.
I'm not here to kill it. I've got to give it a chance.
Coming in.
He singled you out.
some examples of each, shown some demonstrations. So just in closing, I want to say that science and engineering and the field of materials in particular has been the basis for much that we have in the modern world, be it the materials we have on our bodies and our clothes, be it our computers, be it our modern infrastructure, be it the projector here, everything around us. Most of these materials have been invented in the last couple of 100 years. We're still inventing more materials. It's unfortunate sometimes we find the materials we invent have side effects that we didn't anticipate when we made them. We have to use science and technology to try to solve those problems. We know, for example, plastics, which have been a huge boon for technology, have also resulted in a lot of complicated environmental problems. But we really only move forward through science and engineering. And I'll leave you with one very short movie clip from Ghostbusters in the words of Bill Murray.
What has that got to do with it? What has that?
Back off, man. I'm a scientist.
Took a little bit of liberty with the subtitles there. So with that, a little aerial view of the University of Maryland campus. And thank you very much for your attention. I'd be happy to answer questions. Please Please use the microphones that are coming around. I will deal with that, Dave. Oh, yeah, we want to keep the front free. We don't want to get in trouble. Please use the microphone if you have any comments or questions you'd like to put forward.
Donna?
What's that? Yes, UMass Amherst.
While you're looking over there, what percent of the people come to you and say, could you find a material that does this, versus, hi, this is really neat. I bet you there would be a use for this.
At the university, we spend most of our effort in basic research looking for new materials and trying to understand the properties of the materials we have. Some examples that have that are coming out of the university right now, we have a strong effort in taking a natural material, wood, and modifying it to make materials that are essentially a wooden material that's essentially as strong as steel. In fact, they've just built a pilot plant in Frederick, Maryland to manufacture this super wood material, commercialized out of technology from the University of Maryland. We're also working very hard on new materials for battery technology that would hopefully allow battery charging and discharging at lower temperatures, so you don't get stranded in Minnesota in the winter in your electric car. We're also working on fast charge materials for batteries, so you can charge your car in 10 minutes or less. And then finally, ones that could have higher energy density, so you could go 400 or 500 miles on an electric charge rather than 200 or 300. Other examples are new catalyst materials that are being worked on. So those are just a couple examples.
This is a bit of a frivolous question.
Yeah, it's on.
Yeah, this is a bit of a frivolous question, but I would love to do some of these experiments with my grandson.
Yeah.
Could I go out and buy polymer someplace?
Yeah, there are places on the web you can buy many of these examples. Yes.
And the magnets and the
upper
pipe and all that.
Yeah, I would. Yes. Well, the pipe comes from Home Depot. There's a website, amazingmagnets.com. You can buy amazing magnets. .com, where you can buy magnets. When they get this is even at this size, which is a 3/4 inch diameter, they become a little bit dangerous because they're so strong. So I might recommend a smaller size magnet, depending on the age and that kind of thing.
Can you speak briefly about nanoparticles when they first were being explored with regard to lotions and makeup and that sort of thing?
For example, silver nanoparticles are known to be antibacterial, and so they've been used in various applications for antibacterial properties. And then sunscreen typically has titanium dioxide nanoparticles in it. What's not well understood, though there's work on it, is the influence of nanoparticles on the body, because how they pass through the cell wall and get incorporated in the body is something of current study and concern in some cases. And so this is something I know the FDA is working on and worrying about. Over here first.
You didn't mention carbon nanotubes.
No, I didn't.
Did they fail or what?
No, they're around. They're being used for a range of things. Surprisingly, if I just jump up here, this actually. This is this image down in the corner here is a high resolution image of a carbon nanotube with buckyballs inside it, which are carbon spheres, taken by a faculty member at Material Science and Engineering at the University of Maryland. No, there's still a lot of interest in carbon nanotubes, both in composites, in electrical applications. People are trying to make circuitry using them. I remember a company that was formed and I would believe was trying to commercialize large-scale production in New Hampshire. They were asked about could they make a cable of carbon nanotubes for an aircraft carrier arrest system. At the time, they did a calculation, and they said it would take them every furnace they had working 24 hours a day for 8 or 9 years to make one cable, and so it didn't seem viable at the time. But this was probably 10 years ago. I actually don't know if that company is still in existence at the time. But
I recently heard that somebody was doing research on biodegradable plastics.
Yes.
What's the state of that research, and do you expect that it will help to solve our plastic trash problem?
That's a complicated question. So there's two aspects that I can comment on. One is some of the biodegradable plastics were made by taking the polymer chain, like I have here, and incorporating a different monomer periodically along the chain. So imagine putting a red bead occasionally that would then degrade in the environment. And that just meant the polymer chain fell apart, got shorter, but didn't really go away. The more effective model that people are using is, how do I take a polymer and convert it back to the fundamental basic monomer building blocks, and then if I need more polymer, just make it again. And so it becomes a circular process where you make the you have to make the polymer the first time, but then you can keep recycling it effectively over and over again and not put it in a landfill. Fundamental problem with polymers actually relates back to entropy, which is that if I have different polymers and I try to make something out of them, a secondary item, I made my milk bottle, and I've made my plastic wrapper, and I've made my shoe sole and things, and then I collect them in a recycling stream and try to make something out of them. Most polymers are incompatible with each other. So that's why they stamp that number on the bottom, 1, 2, 3, and sort them. But even then, it turns out that only some of those polymers are readily recyclable. So there's a lot of research in how do I take a polymer and break it back down to its fundamental building blocks, allow me to remake the polymer again with the same properties and not have to go back and refine more oil and just put it in a landfill. And that's called, in many ways, the circular economy. And it applies not just to polymers, but to many different materials. We actually had a project at Maryland where people were using a technology developed at Maryland to break down polymers and convert them back to monomer very efficiently. And there's been a couple publications on it, and there's been a small startup that's formed around that as well.
Last question, please.
You mentioned carbon dioxide sequestration. Is that moving along, or carbon sequestration?
Yeah, it's not something that I've been involved with much. There is a faculty member at Maryland who's proposing to grow trees and bury them in the ground to sequester carbon, which is kind of an odd thing, but it's getting a lot of publicity right now. It doesn't strike me as maybe the best way to do things, but there are numbers of other technologies for carbon sequestration, usually involving putting it in the ground in some manner.
Okay, let's thank Rob again.
Thank you.